Hi, welcome to another episode of Hack a Week. I'm back in the workshop. I finally got it all cleaned up, came back from vacation and took a big break from doing anything in here. So now we're back into some of the electronics projects. This week I've got a little project I'm doing on the side for a community college, and I thought I would share it with you because it involves one of these. This is a rotary switch. A little bit unlike your basic toggle switch, and I thought it would be a good opportunity to tell people about a rotary switch and how they work. They're really simple, but there's really not a lot of stuff out there on the internet about rotary switches, so that's what we're going to talk about this week. So let's get started on this project. So here's the device that we're going to modify this week, we being Lisa and myself, and I'm going to let Lisa now explain just what the heck this thing is.
So I run a program where we introduce people to different careers, and one of them is green jobs. And so we talk to people about different ways of having green jobs, and some of them is working in energy. So this is a hand crank where they can use their own energy to crank up the light bulbs. You can see that this one's kind of hard.
How many milliamps is that pulling? Quite a few. About 250 to 300 for an incandescent bulb.
When we move it to the compact fluorescent,
Lots easier to crank and a lot less power required, only about 100 milliamps.
and we were very lucky to have this donated to our project, but one of the things we'd really like to incorporate is LEDs into it. LEDs are made right here in North Carolina, and we'd like to promote that as an opportunity for people to have jobs. And it's kind of also been a criticism is that we don't have that in here. So we're going to take the opportunity now to add LEDs to this educational display.
And that we are. So my job is to mount this LED light. This is just a light that replaces a standard incandescent bulb, got the same base on it. I need to put it on this board, and then I need to mount the rotary switch on there because we're going to have three things to choose from instead of just two. Right now this has just got a double pull, double throw switch, so it can only operate two different things off from two common wires. But this rotary switch will allow me to select three different things, so I think I'll get the LED mounted where that switch is now, and I'm going to put the switch to select everything right here. But before we do that, you're probably wondering what's inside this black box. Well, I'm going to pull the cover off now and show you, and I think it's going to surprise you. Okay, I've removed a couple of nuts that hold this on. I got the handle pulled off. Now let's get the cover off. Let's see what we've got going on here. Look at that. It's basically just a Dayton gear motor. That's all it is. It's a DC gear motor. And because it's a gear motor, when you crank on that end of it, you're really spinning up this motor, and as I've explained with stepper motors, they can be used as generators. Well, so can a DC motor. When we spin this, we're spinning this motor, and the poles inside, the magnets and the windings, move past each other, and because of induction, it creates current that comes out of these two wires. So that's all this is a gear motor. Not really a generator, a motor turned into a generator. Okay, let's put it back together now and we'll try out that LED light. So here's our three bulbs, the LED bulb, an incandescent bulb, and a compact fluorescent. I couldn't help but notice how heavy this thing is, and I realized this is metal. It's like a heat sink around this because there are some high intensity LEDs in there. I got my scale here. Let's just for fun compare 7.1 ounces that thing weighs. Compact fluorescent is about 1.6, and then a conventional incandescent is 1. So anyway, it's pretty heavy. So if you use these, I don't know what you may put them in, bear that in mind. Let's put it in here now. We'll see just what happens when we turn the crank. You want to turn on the crank, Lisa, and I'll observe it. Whoa! It's bright. Look at that. It's really bright. It's only pulling less than 100 milliamps. It's really easy to crank, isn't it?
Oh yeah.
That's way cool. Alright, now let's start modifying this board. The socket is mounted. That was really easy. I just took out the switch and mounted the socket up. Right there, you can see the wires coming out of the bottom. Later we'll go over the schematic for this. Now I need to mount this rotary switch right there. Right about there. I'm going to use a 3/8 drill. And we're just going to wing it right about there. Uh-oh. Got to change batteries. Okay, new battery installed. Let's finish this up. Okay. I've got that hole, but as you can see, this is not going to come through far enough. So what I'm going to have to do is take out my flat bottom bits here, paddle bits, and I need one big enough for that to countersink into. So I'll use the 1.5" paddle bit on the bottom of the board. And what that'll let me do is effectively make this board thinner. And the way that'll work is I'll just drill right into here with the paddle bit, and it'll countersink the whole switch for me quite nicely. I really should have done this ahead of time, because now it's going to be hard to keep it tracking properly. Oh yeah, a lot of fun. See, that's what happens when you forget to drill it ahead of time. Whew, boy, that was crazy. Alright, for future reference, that hole with the paddle bit should have been drilled first and then drill the 3/8 hole. I don't know what I was thinking. I did that backwards, but hey, I'll show you that mistake so that you don't make the same one. Now I just need to locate this in there in the proper way, because it's got this little notch right here built onto the switch, and what that does is it keeps the switch from rotating around. Even if that nut is tight, every time you move this, there's a chance that the switch might, move around, and we don't want that. We want it to stay good and solid so that it'll click its way through. So I need to drill a little hole that can locate into and keep the switch from turning. There we go, the hole's drilled. A little bit sloppy, but hey, there it is. And there's the little locating pin. There's the hole for it. And we'll put that in there. Put the washer on and the nut and tighten it down. And since we have that pin in there, it makes it a little easier to tighten it up too. It isn't going to rotate anywhere. There we go. We'll put the little knob on and click it all the way to the right. And then I'm going to put, I think I'm going to do it so the knob is pointing towards you, and then we could label it right here. And if they label it at all. So there we go. That's that. Now we wire it up. Let's talk rotary switches. This is a double pole, triple throw rotary switch, just like the one I'm using. Double pole means there are two places where you can have inputs, two different sources. They're isolated from each other. Those are our two poles. Triple throw means that you have three choices of outputs. So I can have three loads on the switch on two different sides. So it's as if it's two separate switches, in other words, in one switch. How does it work? Well, when it's rotated all the way this way, let's just say all the way clockwise, between this common and terminal 1 we have continuity, and between this common and terminal 1 we have continuity. Now if I rotated it to the middle position, I would have continuity between common and terminal 2 and common and terminal 2. If we continue to rotate in the counterclockwise direction, I will have continuity between the common and terminal 3, and over here between the common and terminal 3. That's basically it. That's how they work. And these come in all kinds of configurations. They come in, sometimes you'll have 4 poles and 5 throws, 5 different outputs. They were used a lot in electronics before computer soft touch switches started to come into play, where a microcontroller was actually doing the switching for you digitally. So in a lot of old home stereos and such, the selector knob, there was all kinds of switching going on in there. Some of those things would be like this long with all kinds of terminals all over the place. So there's the basics of how a rotary switch works, and now we're going to solder up the one on this project. Here's a schematic I drew up, and this is just like the picture I just showed you on the whiteboard, and this is how it's all going to operate. The generator's here. The output from the generator has 2 leads. One of them runs to one of the common terminals. The other one runs over to the amp meter, goes through the amp meter, comes out, and goes to the other common terminal. And then just as they are labeled, the lights 1, 2, 3, and the terminals 1, 2, 3, so goes all of the wiring on each side of those 2 poles. That's about all there is to it. And the generator, by the way, puts out AC voltage, so it wouldn't really matter which way you rotated it, you would still have the lights light up. And now it's time to solder all these mess of wires up. I've pre-tinned all of the ends of the wires, so that'll help a little. And I'm going to pre-tin all of the leads now on the switch. Get a little heat there, and then apply a little bit of solder. Solder, as we say in America, solder as the rest of the world properly pronounces it. Ha! Doesn't take long to get those tinned, and it just makes for a pretty simple joint. Some people like to run the wire through the little hole in the terminal. If you have small enough wire, sure, but this wire is pretty big, so I'm just going to tin all these, and then I will solder everything up. I get my schematic here to the side. You can't see it, but I can. Okay, here we go. There we go, all soldered up. Now we'll just tidy these up with some wire ties, and we're done. Right, this project is done. Let's try it out. Let's turn on the incandescent first. Wow, that's really hard to turn. To get that much light, the meter's reading about 400 milliamps. Now let's go to the compact fluorescent. Ooh, a lot easier to turn. That's about 60 to 70 milliamps to get that much brightness. And let's go to the LED last here. Super easy to turn. And about 85 to 90 milliamps. A little bit higher on the milliamps, but much, much more light output. LEDs are pretty cool. I think people are going to start using those in their house a lot more in the future. Lisa found this really cool data sheet. Check this out. An LED costs only about 32 bucks a year to operate. A incandescent bulb, $328 a year. And a compact fluorescent runs about $76 a year. I think they base that on about 3 hours a day of usage. And also the environmental impact is, I guess, quite a bit less. These have mercury in them, like a lot of people know. And let's see, carbon dioxide emissions from, I guess, the the waste and the making of them. Only 451 pounds a year for the LED. Incandescent, about 4,500 pounds a year. And the compact fluorescent, about 1,000 pounds a year. So there's some numbers for you to crunch on. Anyway, this was a pretty fun little project, and I hope you learned how to work with a rotary switch. So, there we go. Until next time, keep on hacking.